This is Mrs. O'Neill for AP Chemistry, Chapter 6, Section 3, Line Spectra and the Bohr Model. In this section, you should be able to understand how light is really simulated by this line spectra, be able to understand that electrons exist at certain energy levels, and it's called energy levels because electrons move between energy levels by the use of energy. And of course, how this Bohr model helps us understand where these electrons are and where they're moving. So again, I suggest you to pause the video, fill in the blanks, and then play to hear my words. So Planck and Einstein gave us the how electrons are arranged in an atom, but then Bohr offered this line spectra. So there's Mr. Bohr himself, pretty handsome. So this line spectra is the source of radiation that separates the wavelengths. So again, there's that range of frequency as well. And so then all the colors are possible, like the rainbow, red all the way to purple. And of course, there's different variations of the red and the orange and the yellow and the green and so on. So if we look at the, like a prism, right? So if we take a light source and we put it through a slit, and take like a prism, it's going to show us that rainbow of light, anywhere from, again, red to that purple, but there's all these different shadings as we go through. And that's why all elements, when they give us their spectrum of light, they're all different colors. Okay, so this line spectra, again, is a spectrum containing radiation of specific wavelengths, which means gives us frequencies. So if we look at the fingerprints of elements, and we look at, here we have two. We have hydrogen and we have neon. So notice how different their line spectras are. So if we were to look at a tube through like a slit or a radiation, give it some energy, we would only see these 1, 2, 3, 4 for hydrogen, and that would be the fingerprints at certain wavelengths. Now for neon, notice there's not even any purple, but then you have these bluish aqua, a little bit of green, some yellow, yellowish orange. Wow, you have a lot more lines or a lot more line spectra of neon. So this is another way to identify elements in the gaseous form, exciting those electrons and seeing how they're moving from one energy level to another. So if we look at the hydrogen spectrum again, so this emission spectrum, because there are colors and it's given off when we excite these electrons. So in this case, there's very few discrete lines shown. Again, there's only the 4. Here, this is a really cool periodic table that I found. This is the spectrum, or the line spectrum, the electromagnetic spectrum of every single element. I think that's pretty neat. Now, it might be hard to see some of them. Again, for hydrogen, you should see more or less 4 lines, so it might be a little bit harder to see just because of the picture. But I think it's pretty interesting how some of them hardly have any lines, and then these transition metals, man, look how cool those line spectrums would be. So what's the difference between absorb versus emit? Well, what we see is really the opposite of what is being absorbed. Let's think Thanksgiving. So cranberries are usually red. So what happens is we're absorbing a lot, again, looking at the graph, we're absorbing a lot of that like reddish area, but we're not absorbing hardly any of the red. So again, it's the opposite. We see the red because the green is being absorbed, okay? Same thing with spinach, right? So if we think about spinach, if we go over here, right? If we think about spinach, very little of the green is actually being emitted. Most of the red is being absorbed, and the green the green is being emitted, but that's because, again, we see the opposite of what's being absorbed. I thought that was pretty neat since we're close to Thanksgiving, or just past it, depending on where we are in the course. So only certain energies then are allowed for the hydrogen atom, okay? So you can only give off certain amount of energies. And again, we're going back to the energy equals Planck's constant times frequency. So again, this energy is quantized, okay? So then Bohr came up with the idea where these electrons have a certain amount of energy, and they are going around the nucleus like the solar system, okay? So let's think about this. Speculate as to how Bohr's model explains the fact that hydrogen gas emits a line spectrum rather than a continuous spectrum? Well, again, these photons are only allowed certain frequencies. They're only allowed a certain amount of frequency that can be absorbed or emitted as that electron changes between energy states, between like a ground state and an excited state. So these lines in the spectrum correspond only to certain frequencies. So again, this energy state of this hydrogen atom. Now we want to remember that hydrogen only has one electron, okay? So this first quantum number, or N, represents that energy level. So, and again, there's a ground state and an excited state. So this Bohr ring, or you want to call it, right? He didn't know why, but only certain energies were allowed at certain energy levels, certain energies for certain energy levels, for certain frequencies, certain wavelengths. So now things are starting to come together. So putting energy into the atom, move the electron away from the nucleus. Okay, so if we're putting energy into the atom, that means those electrons are absorbing that energy, going from its normal ground state to an excited state. So that actually isn't the big deal. The big deal is when those electrons return to its ground state, that's when they're giving off that light, the light that we see in those different colors, okay? And those colors, again, represent the different energies, represents what's being absorbed versus what we can actually see. So the color is also going to depend on how high those electrons move to. So let's say we go from energy level 1 to energy level 2. Again, not a big deal, but when the excited electron goes back down to its ground state, it's going to give off red light. But how about if an electron in energy level 2 jumped all the way up to energy level 4 and now is jumping back down to its ground state of 2? So this is a difference of 2. Now it's going to emit some purple light. So let's look at here. Ooh. So let's go back 2 to 1. So if we look here, this 2 to 1, that electron is in the second energy level going down to the first energy level, and it's going to give us some red light. And if we look at the other one, 4 to 2, so now we have an electron from the fourth energy level all the way back to the first energy level, or the second energy level, is going to give us this kind of purplish color. So again, we want to remember, here's our ground state. It's absorbing energy going up, right? It's absorbing energy when it goes from ground to excited. But once it's excited, it's going to emit. It's going to give us this light energy, okay? So again, it's energy, but it's light energy, and we can see it in different colors. So black light, if you want to read this information, that's fine. It's just a little extra information. And I thought this was neat because this is an element you don't really see too often or hear too often, but this europium also gives off certain colors depending on on its fluorescent glow. So then what does this Bohr atom give us? Again, it gives us the fact that electrons are on energy levels, okay? And this information is not really on your reference sheet, but we want to understand where this Bohr model came from. So when the electron moves from one energy level to another, again, like everything else, final minus initial will give us that change in energy. And remember, that's a state function. Doesn't matter where it started or where it ended, or I should say it does matter where it started and where it ended, but not how it gets from one place to another. Doesn't matter the path. So then when is this actually true? Oh man, look at this. It's only true for hydrogen because it has a monoelectronic species, right? Monoelectric, it only has one electron. So why the negative sign? Because again, to increase the energy of the electron, it's further away from the nucleus, okay? So the maximum energy an electron can have really is 0, right? At an infinite distance. So the limitations of this Mr. Bohr model that he came up with really doesn't work for any other element except for hydrogen. And we want to remember that electrons really don't move in circles. Remember, they're moving all over the place. They're going up, down, left, right. Remember, electrons or atoms are spherical. right? They are not like a solar system and you're going around the nucleus. So we have to keep that in mind. So his model worked for a little bit of time because he dealt lots with hydrogen. But when it dealt with other elements, then it was very, very limited. And now we had to go to other ways or other understandings of what's going on here. So as the electron in a hydrogen atom goes from 3 to 7, does this mean it's going to absorb that energy or emit that energy? Hopefully you said absorb, right? Because we're going from 3 to 7. We're going from a ground state to an excited state. So it's absorbing that energy going from lower to higher. Okay, see you in class.